Perfect. Welcome everyone to our bi-weekly CySR seminar. This is our second since the spring semester has started, and the spring is looking more like a spring now with the temperature getting warmer, except for the snow we had yesterday. I hope your semester is going well, your classes are going well. We have this going on every other week, but occasionally we also want to make sure that you follow along what happens at Viceroy at large. So there is this virtual series. So we had one in end of January, and there is one coming up next week. So I would like to encourage you to attend that as well. So today we have the great pleasure of having Dr. Yong Wang. Steve is also how he goes by first name, who is a professor and also department chair at the Department of Computer Science at the University of Idaho. Dr. Wang holds a PhD in computer science from the University of Nebraska-Lincoln, and he has over a decade of experience in industry before he decided to transition to academia, for which I am very grateful and wonderful thing to see. His research area focuses on security and privacy in IoT, cyber physical systems, cyber infrastructure, and adversarial machine learning. He has come and joined the University of Idaho very recently, and I'm very pleased that he has also stepped in to be the site lead for the CySR program at the University of Idaho. University of Idaho is one of the founding members of our CySR consortium, and Dr. Jim Alves-Foss was leading that effort until this year. And Dr. Wang has now taken over that and has recruited students, and the program is going well there. Today, he will be speaking on a topic that is near and dear to our heart in the CySR program on securing machine learning and AI in general, and that will be the subject for the day. He will be talking about evolving threats, attacks, and defenses. I am very much looking forward to what he has to share and to learn from it. And so I'll be paying close attention and taking notes, and I encourage you to do the same. If you have questions as the presentation goes, you can put them in the chat. James and I will be monitoring them, and you'll get a chance to answer the questions to be answered by Dr. Wang at the end. I also want to remind you before you leave, towards the end, there will be a feedback we would like to get from you. So James will put that link and make sure to complete that. With that introduction, I'm very much grateful, Dr. Wang, that you joined today, and the floor is yours.
All right. Thank you so much for the introduction. Thank you. Thank you for the invitation as well. It is my pleasure, to introduce my recent research on securing machine learning, evolving threats, attacks, and defenses. So today's discussion will cover a few areas. So we are going to talk about secure machine learning in general, and one of the specific attacks we are going to explain here is a specific attacks against hypersphere models in machine learning. So we're going to see a little bit more details, and we're also going to talk about another delta evasion attacks. This is also come from our recent research in the last 2 years. And in the end, I think I'm also going to talk about defense mechanism in machine learning and so on. So speaking about attacks, I think we know attacks focus on the vulnerability of the system. And we can also look at the different types of the vulnerabilities. On the slides, I think you can see here, I list 3 different types of vulnerabilities here. We have the software vulnerabilities, and there are so many examples: buffer overflow, SQL ejections. Those are examples of the software exploitation, software vulnerabilities. And we also have the hardware vulnerabilities. A very good example for the hardware vulnerabilities includes spectral and meltdown vulnerabilities in the hardware level discovered in 2018. And on the other hand, Agrom themselves, it also includes vulnerabilities. And we know machine learning and AI, it is a very hot topic right now. If you go to any conferences, it seems every papers, it has a portion of the machine learning and artificial intelligence. And for the AI and machine learning, they are heavily rely on the algorithms to work perfectly. And in 2014, I think there was also some of the research who have been studied and discovered that algorithm it may also include vulnerabilities. So we're going to see some of the examples in the next few slides. Generally speaking, machine learning has gathered lots of attention over the recent years. And in the cybersecurity areas, we talk about how to use machine learning and AI to automate cyber operations. We also talk about how to use AI and machine learning to help the cyber defense, such as malware analysis, intrusion detection, and so on. And at the same time, the use of the machine learning also raises a lot of attention to security in machine learning and artificial intelligence themselves. So here I give you a few examples. For example, in the Tesla's autopilot system, this is from the official Tesla's website. Their self-driving vehicles include 48 neural networks that make 1,000 predictions per timestamp to autonomously operate motor vehicles. And machine learning and AI, it has also been widely used in the healthcare areas. In August of 2020, there is a big company, Sanford Health, and they partnered with another companies. They are talking about they want to use all the clinical patient data as a training and trying to develop more intelligence from those patient data. So these clinical patient data includes image, waveforms, and structured health records. So that also bring a lot of issues and what are the privacy of the patients. Can any companies using the patient clinical patient data for training purpose? So we also know the generative artificial intelligence, it has been very hot in the past few years, and some of the large language models, they also use crowd sources such as Wikipedia. And we know the Wikipedia it's maintained by the communities, and there is also one of the attack, which is called a boiled frog attack, that also raises some of the question about where we can trust the information from the public sources, such as Wikipedia here. So before we introduce some of the attacks, I just wanted to share with you some of the adversarial examples here. So these adversarial examples is coming from our research. And if you look at these four images here, they looks exactly the number 8. And however, for these four images, only the first one, it is the original image. So there is this will also be recognized by the training model as a digital number 8 here. And if you look at the second image here, this image it is exclusive OR with the original image and also the perturbations we see from here. And as you can see here, the perturbations we injected into this second image, it's very minimum. It's just one pixels there. But however, and these pixels will mess up the machine learning models such as the decision tree, and using the trained models, normally it's going to recognize the original image as 8, but with these perturbations, and it's going to recognize this image as number 2 here. So this is the decision tree, examples, and we also apply, the some of the attacks on random forest and also the adaptive boosting ensemble as well. You can see the perturbations we inject into the original image, and with the perturbations, even though these numbers still looks like 8 to us, but the machine learning model is going to recognize them as number 2 here, right? So this is a very simple adversarial example, and we have seen from many other similar research as well. So, you may think about that, oh, that is not a big deal, right? It is just a image 8, with some perturbations. Then, the machine learning model may recognize this one as different numbers. However, if you look at this next the adversarial example here, so this really cause a lot of concern here. And when you look at these examples, and on the left side, you just see 2 stop sign here, and it fills both of the dirty street sign. However, if we use some trained model to recognize the image, and what we're going to find out here is the first one, the stop sign on the left side, it's a real dirty stop sign, and the machine learning model does not have any issues to still recognize this as a stop sign. But however, in the middle of this image, the stop sign with some of white and also the black stickers, and using some of trained machine learning models, that machine learning model will recognize this stop sign as a speed limit 45 miles on the street. So now it really raises some of the concerns about machine learning security here. As we mentioned earlier, Tesla does use the neural network to do the predictions, like recognize the stop sign, recognize the speed limit, and so on. And if this happens, to some of the neural network models, it's going to raise a lot of concerns whether machine learning security, how important it is to study the machine learning security. So this is another adversarial examples, and which is also based on previous research in 2018 areas. So there are many different types of adversarial machine learning. And generally speaking, adversarial machine learning investigates the security of machine learning methods against several attacks. So when you think about the adversarial machine learning, it studies the adversarial attack. For example, how do you manipulate the input to force the machine learning or AI to make the wrong predictions? So that will be the adversarial attacks. Adversarial machine learning, on the other hand, also study the defensive mechanism and what machine learning models can do to prevent the adversarial attacks. So those are the scope of the adversarial machine learning here. So again, for the adversarial attack, and if based on the knowledge of the models, there are black box, the testing, white box testing, or gray box testing. For the black box testing, basically, you know nothing about the internal machine learning models. You don't have access, to the internal data structures used in the machine learning models as well. So in the white box, the testings, we assume we know that machine learning models. So we also have access, to the, for example, the trees, or internal data structures built for those machine learning models. So gray box, the testing is between the black box and the white box there. Based on the attack goal, there will be targeted attacks, and you want to force the machine learning model to make a target output. And for the untargeted attacks, you just want to make sure the machine learning model does not produce the original results. So that will be the differences between targeted attacks and untargeted attacks. Based on the attack method, there are also many different adversarial attacks developed here, like a fast gradient assign method, Carnini-Wagner method, and so on. So there are many different attacks which have been discovered for adversarial adversarial attacks. On the defensive side, we're going to have short discussions later, and defensive mechanism can be based on detect the adversarial attacks, prevent adversarial attacks, and also based on some regular like risk mitigations we applied like in our operation technology and information technology here. So here, I think this is one of the threat models we developed for studying the security of the machine learning. And just like we do the security studies in some other cybersecurity areas, we want to understand the attack surfaces. We want to understand attack vectors here. And here, I think we want these models shows everything here. So when you look at these machine learning models, and the first thing I think we are trying to find out here is what might be the input to the machine learning models. And the machine learning models we consider here includes supervised machine learning, unsupervised machine learning, and also the reinforcement learning as well. So if you look at the input to the machine learning models, the one type of the input, we call it training data. So these are the training data set you provided to the machine learning. And the second part of the data to the machine learning models, we call it inference data. So this is also the fresh data, right? You provided to the machine learning models based on the trainings, you create the models, then you provide the fresh data, and the machine learning models is going to make the predictions for you. So that will be the inference data, fresh data we talk about here. There is also the third type of the data. We call it interaction data. And for example, for the reinforcement learning, lots of time, reinforcement learning also use the interaction of the machine learning models with the environment and to collect all the information as the input so they can continue to refine the models and make the models better here. So the input will also be the interaction data will be the other type of the input to the machine learning models. And the last one, apparently, the machine you provide input to the machine learning models. The machine learning model will also produce output for us. The output could be the prediction, decision, policies, and some other things. So many attacks have been discovered targeting to the security of the machine learning. And so here, if we look at the training data set, this will be also part of the attack surface for the machine learning model, because if some of the malicious adversaries, if they modify the training data set, right, and that's going to mess up the machine learning models you build. So the training data could be part of the attack, the surface. And also the input, the fresh data, it could be the target as well. As the adversary examples we discussed earlier, so if some malicious actors inject the perturbations into the fresh data, it may also mess up the machine learning models here. And so that will be the second part. The inference data is also part of the attack surface. And the third part is the environment data. And environment data, it also can be manipulated by the malicious user as well. And there are some research work which has been done, like what can they do to intervene the interaction process, so the machine learning models may make some different predictions there. So there are some research which has been done as well. And when you look at these attacks, some of the attacks targeted to the training data, such as the data poisoning attack, some of the attacks targeting to the input data, like they want to modify the input to the machine learning model to force the machine learning model to make the wrong predictions. There are also data extraction attack. So malicious advisors can extract the training data from the machine learning model. There are also like a model extraction attack. So the malicious users can extract the critical parameters from the machine learning models, so they can copy and clone their own models. So that will be the model extraction attacks. So this model just summarize some of the attack services and also attacks in the machine learning here. So we also did one of the taxonomy for the threats and attacks targeting to the machine learning, and we list a few of them here. So there are threats and attacks which can be divided into exploration category. It can also be divided into exploitation categories. So for the exploration category, this is more like the passive attack or eavesdropping attack. They want to steal the model parameters. They want to steal like the training data from the models without force the machine learning model to make the wrong prediction. So that's why we call it exploration attack. And for the exploitation attack, generally speaking, they involve inject perturbations into the training data set, and force the machine learning model to make the wrong predictions here. So in this part of the presentations, I'm going to talk about the 3 different types of the attack and model inversion. So basically, we want to show that the malicious adversaries, they actually can infer sensitive information from the about the training data from the machine learning models. So that will be the model inversion. And we have the parameter stealing, so they can steal the critical parameters from the machine learning models, and then they can clone their own machine learning models, parameter stealing. And we also have the data evasion attack, so they can malicious actors can inject the perturbations into the data set and force the machine learning model to make the wrong predictions there. So these are the 3 types of the attacks we will cover in this part of the presentation here. So let's look at some of the different type of attacks, and we mentioned about exploring attack, right? And basically, they focusing on extract the critical parameters from the machine learning models, and they also can extract the training data from the models. So one of the good examples I use very often here is if you look at this human face on the left side, and if you look at the figures, this one, it looks very blurry, and this is actually one of the data extracted from machine learning models here. So by doing lots of queries, and eventually they figure out what samples belong to the machine, what samples belong to these machine learning models, and what samples does not. They put all the samples together, so they have this picture here. And actually, if you look at the human face on the right side, that is the actual training data. Actual image included in the training data. So the point here, it brings a very serious considerations. We know the machine learning model and artificial intelligence, they requires lots of the training data. And we also realize that whenever we do the trainings, we need to remove personal and identifiable information from the data set. But as you can see, even with some of the anonymized data, for example, the image here, there is still certain ways a malicious actor could apply to the machine learning models to extract the training data set, right? So this is data extractions we talked about earlier. The second one here is exploitative attack, and by using the the perturbations by injecting perturbations into the delta to the machine learning models, they can also force the machine learning model to make the wrong predictions. So the Panda, this is a very classical examples of the delta evasion attack. So the Panda on the left side, that is the original image, and in the middle, that will be some of the perturbations. And when we put these two pictures together, then we get one of the adversarial example here. So original image, machine learning will recognize it as a Panda, but for this image with the perturbations, the machine learning model, the same model, will treat it as different animals, such as a gibbon here. So there will be a threat to the machine learning here. So one of the attacks I think we studied here is it's exploratory attacks on hypersphere-based model. So when we look at the machine learning models, there is a certain type of the algorithm, such as k-means, k-medoids. They are based on some of the clustering techniques, right? And if you label this one as a cluster number one, if you label another cluster as a label number two, you can also make the prediction as well, right? So we studied these hypersphere-based models, and we also developed one of the attacks against these hypersphere-based models. So in this picture, as you can see, we just doing a very simple study here. So we are going to label all the interior points as label one, and we are going to label all the exterior points such as red as a label 0 here. So the hypersphere attack we talk about here, it includes two steps. And the hypersphere attack is also a black box attack. You actually don't need to access any internal data structure of these machine learning models. You only need to send the query and try to get the response, where that is predicted as label 0 or label 1 here. So this attack includes two steps here. The first one is called reflections. So we're going to go through this step together. So then we're going to move to the next step, which is called infection here. So let's look at the reflections. So when we have an initial point in a hypersphere, for example, if you look at this blue point here, and when you send a query, this machine learning model return, a label like label 1. So this is a part of the clusters. And when we're going to select this this point, this blue point as the initial point, we're going to select a random directions. Then we're going to update this point so we can until we went to a point which is very close to the boundary. So if you add a little bit more, then the query is going to return you like this interior point become exterior point. And if you move it like back, then this machine learning model is going to return you like interior points and so on. So you want to identify a boundary close to the boundary point. And once you calculate this boundary here, and our goal here is trying to find the centroid and also find the radius of this circle here. Because if we are able to find this circle by identifying the centroid and also by identifying the radius, then we actually know exactly how these machine learning models do the predictions here. So what we're going to do here is using the similar approach, and we're going to identify two more points on the boundaries here, like B and C. Now, in the next step, we're going to collect the A and B together, so that will become one of the line. Collect the A and C together, that will become another segment here. Then using some of the geometry, the knowledges we learned from the high school, maybe from some other subjects, and we're going to find the perpendicular lines of the AB and also the AC. And once we are able to find the perpendicular line L1 and L2, and we also calculate their intersections, and based on the calculation, based on the geometry, we know this intersection between the line 1 and the line 2 that will actually become the centroid of this circle. And once we identify this centroid, then we can also calculate the radius from the centroid to B, to A, and to C. You are going to expect the same radius there. So using this reflection process, and we will be able to identify a circle, or maybe you can call it a clusters in the hypersphere. And you know exactly the centroid, the location. You also know the radius of the locations. Then in the next step, you may wonder here is, oh, we in the hypersphere models there are lots of different clusters, and will you be able to identify all the rest of the clusters? And I think the answer here is yes. So then we'll move to the next step. We call it infection. So infection here is using the knowledge we learn from the reflection, and we are trying to identify more clusters, from these machine learning models. So the process starts like this one, right? So we're going to select one of the points from the clusters you identified. Then we're going to keep move this point outside of these clusters, right? So for example, when you move this one, the D move to another areas. If you send this input as if you send this input to the machine learning models, and this machine learning models, it may return you, oh, this is going to be the interior point, or this is going to be the exterior point. If D is also an interior point, not an exterior point, so that tells you D is outside of this cluster, but however, D is also labeled as an interior point. So there is only one reason, to tell you why it can happen, because D, it can be located in another cluster. So now you find another point from another cluster. And from here, you can repeat, the reflection process we discussed earlier, and you will be able to use the same reflection process to identify the centroid and also identify the radius of the new clusters. So if you repeat, this process, reflection, infection, and eventually, without learning, how this hypersphere model works, and you will be able to get lots of the circles, their centroid and their radius and so on. And even without using the models, you can do your own the decisions, whether that will be the interior point or that is the exterior point, right? So hypersphere attack, it is a black box attack, because you don't need to know anything from the machine learning model itself, as long as you know that it is based on some cluster-based techniques there. All right, so we evaluate these hypersphere attacks using some different data set. For example, we use a randomized data set, just include two features, X coordinates and Y coordinates, which includes 25 hyperspheres. And we also use one of the data set, which includes more features like RT, IoT 22 data set. And we also use applied the hypersphere attacks on another one. It's the UCI, the digits, the data set, which includes about 64 features and 3 hyperspheres here. And here are some of the evaluation results for this hypersphere attack. So when we apply the hyperspheral attacks on these simple, the randomized, the models, and we are able to successfully collect all the white circles here, right? So if you look at the white circles here, these are all the centroids we have been successfully identified from testings, and after we looking into the randomized the machine learning models themselves, we also noticed that some of the clusters we didn't capture from the attacks. So if you look at all the green circles here, those are the centroids we did not capture during the attacks. But however, if you are able to scan the space sufficient, and hopefully that will also be able to capture the green circles, those centroids as well. So this does show this hyperspheral attack, it's effective on some of the hyperspheral based machine learning models there. Another one, the second evaluation we did here is we evaluated the hyperspheral attacks on the RT IoT 2022 the data set as well. And from here, what you can see here, there are some of the initial samples, and when we do the testing and we found that they are mislabeled, basically the machine learning model give you the wrong predictions. So we select these points as the initial points. Then we launch the hyperspheral attack, and eventually we are able to capture some of the centroids. And when we look at all the centroids, then we compare the captured centroids with the original centroids from the machine learning models. And here you can see the distance. So basically, it's a Euclidean distance and between the original centroid and the captured centroid, and also the initial points here. And now you can see the captured centroids, their Euclidean distance to the original the centroids, it's a pretty small. So that also shows that we have the hyperspheral attacks. I think they did capture the centroids of those clusters, and you can also tell that why these points have been labeled wrong during the initial testing phases. Because if you compare their coordinates with the original centroids and the Euclidean distances, it's a little bit large than normal. So that's why they have the wrong predictions there. So that will be another evaluations we did on the RT IoT 22 data set. Then I think we last example here, we evaluated the data set, evaluated the hyperspheral attacks against the UCI, the DIGIS data set. And one thing we it's very interesting here. Now we started with the initial sample, which is the line, and when we use these examples, use samples to find all the centroids in the machine learning models, we eventually find another like the clusters. And if you look at these clusters, and apparently after we plot this new like a centroid from that samples, it shows as a digital 0 here, right? So from here, what you can see here, and actually from the machine learning models, we kind of also did a model inversion attack, because we also extract training data zeros from the machine learning models. So that shows the hyperspheral attacks is not only effective, it can also be used as a model inversion. It could be review some of the training data as well. So those are the three evaluations we applied on this hyperspheral attacks. And so here is the summary of the hyperspheral attack. So it can be used as both a parameter tuning attack, because after the hypersphere, you know exactly where are the centroid of those clusters, and you also know those radius. And by doing exactly the same thing, you can create a models which help you to do the predictions as well, right? And it is also a model inversion attack because we are able to extract some of the training data from the machine learning model as well. And so that will be the hypersphere attacks. So after we studied these hypersphere attacks, we also studied some other like popular machine learning models, such as decision tree, the random forest, such as adaptive boost, the models and so on. And we also studied where we can apply the same things and by doing a delta evasion attack, by injecting the perturbations and force the machine learning model to make some wrong prediction here. And here I want to give you some brief introduction about the attacks. And when we conduct the exploitative attacks targeting to the tree-based models, and our goal here, it follows two principles. The first principle here is called maximize the confusions. So we want to select some of the initial points from them which were confuse the machine learning models. So we are trying to maximize the confusions. The second principle is we also trying to follow here, which we call it's minimize the perturbations. Because when we try to inject the perturbation into the image, we also want to make sure and the perturbations we inject into the original delta, it's minimum. So to maximize the confusions, it has to be based on some of the properties of the machine learning models. But to minimize the perturbations, we're using the Euclidean distance here. So as you can see, this is also a very common parameters. Sometimes it's called L2, the L2 norm to evaluate how change of the perturbations to the original deltas here. So so using the Euclidean distance, we can measure the perturbation here. So here is a simple examples for the decision tree here. And in the decision tree, and this is a very simple decision tree models. And it based on the two features, the X and the Y. If you look at here, and first we're going to compare, the X coordinates. If it's greater than 2, then we're going to compare, the Y coordinates. Based on the Y's value, we can decide where that is label A or that is label B, and so on. So for decision tree, the process is pretty simple and straightforward here. So for the single decision tree, here is one of the attack we talk about here. And the attack, the delta evasion attack we talk about here is based on the white box. It's not the black box as we talked about earlier for the hypersphere attack. So here is the process of the single tree attack. So first of all, find a path for the starting node, right? For example, if you have this is the original X. And when you use the decision tree model, it's going to predict a label for you. And if we assume the 6 is the labels here, and we're going to find this path. So from 1 to 3, 3 to 4, and to the 6. Then if this is the untargeted attack, or this is the targeted attack, we're going to find another path. For example, if this is the targeted attack, we want to modify the delta X to make sure the machine learning model is going to produce a different results like 8 here. So we're going to find the path from the root to the target node. Then as you can see from 1, 3, 4, 6, from 1, 3, 5, and 8, there is a common node here. It's 3 here. And then we're going to find out what features is used to force the machine learning model to take the branch from 3 to 5 instead of to take the branch free from the 3 to 4. Then that that change, that values is going to be the perturbations we're going to inject into that features. And if you are able to find all the possible like the output, for example, anything other than the number 6, then we are also collecting all those adverse samples. Then we're going to compare their Euclidean distance, and because we want to minimize the perturbations, so that way we can select the least changes from these attacks. So this is called a single tree attack. But using the similar approach, we actually can apply to all the other like tree ensemble machine learning models, such as supervised tree ensembles like random forest, adaptive boosting, or maybe unsupervised tree machine learning models, and so on. So the idea is similar, trying to max the confusion and also try to minimize the perturbations there. And we do apply all the attacks against all these approach, all these machine learning models, and eventually we develop a very unified algorithm for each the machine learning models here. And I can also share the slides. You can see the algorithm. I can share the papers with you guys as well. And in the end, I think we did evaluate these evasion attacks on the training the machine learning models, decision tree, random forest, adaptive boosting, and also the isolation forest, and so on. And there are some interesting data. It's very interesting. So here on these slides, and it shows the Euclidean distance. That's the perturbations we inject into the training data set, and we apply it to different tree-based models here. So something is really interesting here is to force some of the models to make the wrong predictions. Sometimes the perturbation we inject into it actually is pretty large. So if you look at the isolation forest tree, this is the unsupervised machine learning models, and the rest of it is supervised machine learning models. But it takes more like modifications to make the isolation forest to make the wrong predictions. So that raises some of the questions. Maybe in the machine learning and the AI models, some of the machine learning models is more resistant to adversarial attacks. Some of the machine learning models may be more vulnerable to some of the adversarial attacks. So that will be just some of the attacks we discussed here. I think we are almost running out of the time, and I will share the slides with everyone if you are interested. But I'm going to stop here in case if you have some questions for me. Yeah.
Wonderful. I did not want this one to stop. It was very interesting to follow. Thanks for an excellent presentation. We do not have a whole lot of time, but I will maybe have time for a couple quick questions. Does anybody have a question to ask? You can unmute yourself and go ahead and ask, or you can put it in the chat, whichever is convenient.
So I do have the references page on the slides. You can find all the related publications. I think that includes all the details there. Yeah.
That's wonderful. So please make sure to send us your slides, and we'll post them immediately, and the recording as well. But is there anybody who has got a quick question? While somebody thinks of a question, let me ask one. So the attacks, the hypersphere attacks you discussed earlier, makes an assumption. It's like dividing up the world into circles. Like some of them could be big, some of them could be small, some of them could be overlapping and things like that, right? And without knowing anything else, the attack would construct this basically so that the decision will be made whether they are inside or outside for everything, right? I'm not like going to make your attack even stronger, but is there, and I could see the beauty of the geometry computation there and thinking of these things as circles, but clearly that's an approximation. The reality is not going to be circles. These clusters are not going to be circles, right? So is there anything you have considered into making these other geometrical things, or are you satisfied with the results you are getting under the assumption that your clusters are circles?
So I cannot clearly hear your voice here. Sorry about that. But let me try to answer here. The hyperscale attacks based on if you know this is a cluster based algorithm, then the hyperscale attacks it's pretty effective there. And one thing I think I want to point out here, that's also something. The study of the adversarial attacks against machine learning and AI, I think it is still in its infant the stage. And because we all work in the cybersecurity areas, then we want to know that are there any like the real attack scenarios people may use the adversarial examples to mess up intrusion detection, intrusion prevention, and those things there. And I think the theoretical study is just review that we do need to pay attention to the machine learning security and also vulnerabilities in the algorithm. But I think there is still steps away to like very realistic cyber attacks against intrusion detection and intrusion prevention engines there.
Yeah, no, I completely agree. And I was just focusing on these cluster-based ones, which is also a significant class. But what my question was, is there anything that you see in the idea of assuming some other shapes for your clusters than circles? Because your method relies on the assumption that clusters are circles, right? That was my question, and probably I know the answer too. It's enough.
All right.
I think it is. Yeah. It is enough for us to go with that because the end goal is slightly different than perfectly recapturing what the clusters could have been. So that's perfectly okay. Is there anybody who had a question? We are running out of time. Thank you very much. I really enjoyed it. It was very clear. And I know the students would benefit greatly from it. Please share your slides and we'll put it up as soon as we get it from you. Thank you for your time today. Students complete the surveys and we will see you in 2 weeks' time. Have a great day.
All right. Thank you.
Thank you, Dr. Wang.